In this video, I want to show you a couple examples of the first derivative test, both so you can see the math and so you can get some kind of helpful hints on how to work through them. So find the local extrema for the function f of x equals x cubed minus 3x squared minus 9x minus 1. Now, because we need to look for the critical points first, that means we need to evaluate, take the derivative, evaluate what the derivative is. So then if we're setting it equal to 0, it'll be helpful to have this factored. So it's going to be x minus 3, x plus 1. And when we set that equal to 0, that means our x's are 0. Our x's should be 3 and negative 1. Now, these are the only places for a smooth continuous function or a differentiable function, which doesn't explicitly say here, but usually you'll have that told to you, or this will be the trick that you got to pick up on. But because it is a differentiable function at all points, these are the only places that the slope might change from positive to negative or vice versa. So if I can pick some value from this side here, I know, and find whether it's positive or negative, I know positive or negative for all of that. If I pick a number between these two, find positive or negative, I know positive or negative for all of this. And something bigger than 3, I know it for all. So I don't need to pick something particularly close to negative 1 or particularly close to 3. And I also don't need to pick two values in between here to check either side, because 1 is sufficient for telling me the whole range. So if we look at that, negative 2 is a nice number to the left because it's not super far, but it's an easy number to work with. Now here is a trick or a way to kind of do this faster, especially if you're doing it in kind of mental math, because we don't care what number this is, we just care positive or negative. So I look at each of these terms. This is positive. Negative 2 minus 3 is going to be negative. Negative 2 minus or plus 1 is going to be negative. A positive number times two negative numbers, whatever they are, will end up being positive. So I know this whole region is positive because I know f of negative 2 is positive, so everything else is positive. Showing that again with the 0, f 3, 0 minus 3, 0 plus 1. 3 is going to be positive, negative. In the middle, we're going to have negative. In the end, we're going to have positive. Positive, negative, positive is going to give me negative. And then f of 4 will be 3, 4 minus 3, 4 plus 1, positive, positive, positive. So that'll be positive there. This tells me that I have a maximum here and a minimum here, because I went from positive to negative and negative to positive on either side of the critical point. If they just asked you to locate or find the x values, this would be sufficient. But because they asked us to actually find the extrema, we need the y values as well. So f of negative 1 is going to be negative 1 cubed minus 3 times negative 1 squared minus 9 times negative 1 minus 1. Negative 1 cubed is negative 1. 3 is going to be negative 3. This will be positive 9, and this will be negative 1. So that will give us a value of 4. And then f of 3, conveniently, we're going to see these first two terms cancel out. (27, 27), negative 27, negative 28. And it's nice that these two, we have a bigger number and a smaller number. Those kind of align with what we'd intuitively expect. That's a good thing to check. If you get something weird, check your math. But it is possible that a local minimum could be larger than a different local maximum. If you want to talk about that in class, let me know. But the long and short of it is we have a local max at negative 1, 4, and a local min at 3, negative 28. And that is our end result. As our second example, find the local extrema for f of x equals x squared plus 2x, x squared plus 2x plus 3, or x minus 1. So what we need to do here is factor this to kind of get it into a simpler form. So that's going to be x plus 3 times x minus 1 over x minus 1. This is a removable discontinuity, is what we've actually discovered. And this means that our we can also then find the derivative much easier by getting f prime of x is equal to, or it's equivalent to, just 1. So if we were to do the quotient rule, it should still simplify similarly, but by doing this algebra first, we got this. Now, if we look here, this means when is x going to give us a critical point? Never. So this doesn't have any critical points, so it doesn't have any local minima, local maxima. And that makes sense because, like we said, this has a removable discontinuity, but it's otherwise a linear line when we do it with a slope, in this case of 1. So there is no local minimum, local maximum, because it's just a line with a hole in it. So I want to throw that in there just as a kind of a different weirdness there, but if you need to go back and kind of see how we work it out, check out the previous example. But otherwise, that will wrap us up here.